Assalamualaikum warahmatullahi wabarakatuh and a very good day to all. So today we are going to start a new subtopic from the compressible flow. That if from the Potter textbook, it will be on 9.3. That is on the isentropic nozzle flow. Okay, so this is the part 3A of this topic. Okay, for the isentropic nozzle flow, actually we are going to cover two types. Either the flow is in a converging nozzle, or it can be also in a converging and diverging nozzle. So if a converging is just this part, okay, so this is for the subsonic, and then it can be also related to either the converging or the and also the diverging nozzle. Okay, where we are going to consider only the gas flow, because we know that gas is easily compressible. So it can be air, it can be any type of gases. Okay, so it has a changing area, like just now I mentioned about converging or converging diverging. So a good approximation, okay, for many flow situation. So we assume that the flow is steady, uniform, and also an isentropic flow. Okay, so this is the a good approximation for actual flow situation. So this is some of the example where we can use this theory in order to study on the or to study the flow, okay, related to this jet engine, okay, any propulsion system like jet engine, the gas turbine, okay. So that is some of the its application. Okay, and if you go to this NASA web page, okay, this learning web page, you can see that this is actually how can be the shape, the 3D shape of this converging diverging nozzle, and why we have to design this kind of shape. Okay, so that's why in this topic we are going to see why we have to design like this one should be the like converging section, and then we have kind of this area we call is a throat area, and then we have this the diverging section. Okay, so we are going to accelerate the flow from the subsonic to the supersonic flow. Okay, that's why we have to design, and we have to know how actually we can get the equation related to this design. Okay, this is in this part. Okay, in order for us to derive the equation in relating this the area change, okay, with the velocity and with the Mach number, and also you can relate with the pressure and also the density. Okay, so we are going to use two equation which are the continuity equation. Okay, and later we are going to look on the energy equation. So this is just a very simple energy equation. So we know that the mass should be conserved, the mass flow rate should be conserved, so we cannot neglect the density change also. So if we are going to consider this area, okay, this part, okay, this control volume in this dark area or channel, okay, so we can we should know that the mass that go in and the mass that go out should be the same. Okay, so this it will actually comply with this continuity principle, okay, or mass conservation. So we can write in terms of this equation. So at this inlet, so it's related to all the properties of the fluid, that is the gas. We got the rho, the A, and the V, and after they got this little bit change, okay, after this at the outlet, okay, there can be a change related to the rho, change with the del rho, and then there can be change of the area also, plus the dA, and then the velocity plus the dV. Okay, V, the big V is the velocity. Okay, this is the rho and this is the area. Okay, you can expand, okay, this equation, and we will neglect the higher order term. Okay, so we just retain the first order term, so we can rewrite back this continuity equation in terms of this expression. Okay, so this is the expression of the continuity equation related to this flow in this area, okay, in this dark channel. Okay, and then okay, so just for your activity, you can just try this, expand, and then you get rid the higher order term and just retain the first order term, and you can get this expression. Okay, why I always highlight about the derivation or derivation. So this is common in fluid mechanics. Okay, we do the derivation. Okay, and from the energy equation. Okay, previously we know that from the equation 4.5.18, when normally we have like in the energy we express in terms of the internal energy and also the pressure energy. Okay, in this case we neglecting the potential energy. Okay, so the we can write this internal energy, the specific internal energy with and also this pressure. Okay, we divide by the rho in terms of this specific enthalpy. So we can rewrite this equation. Okay, and this is also another activity for you. How we are going to convert from this enthalpy to this expression. Okay, so you have to go back to the relationship between this, the thermodynamics relationship, okay, between this enthalpy and also the K and pressure and also the density. So this is also your task. So in the textbook, it just derived in terms of how we can get the transformation from the energy equation with enthalpy with this pressure and also the density with the K value. Okay, so like I said, just use your thermodynamic relation and also the ideal gas equation, ideal gas law equation. Okay, okay, and then we know that we have this Q dot and also the W dot. What does this equation represent? Okay, so this is a question for you, but we should be able that we know that this process is adiabatic for isentropic and adiabatic process. So the Q dot will be equal to 0, and there is no works here. Okay, what is the W dot S? S is referred to what? Okay, so you can go back to the textbook, to the chapter 4, and you can know what is actually the W dot S. So we don't have here in our control volume. Okay, the control volume, we don't have the Q dot and we don't have the W dot. Okay, so we can simplify our equation. So this is get rid equal to 0. So we can just expand. So we just differentiate. I mean, we just categorize. This is at the point 1. All the properties at the point 1, the velocity, the pressure, and also the density at point 1 or at the inlet. And then this is the property at the outlet or at the section. This is section, okay, section 2, okay, of this control volume. Okay, and then we redefine or we express the V2 in terms of the V plus the del V, okay, to just suit with whatever can be changed, okay, after they go out from this control volume. So we just write the V2 is V plus the dV with the change, the pressure P plus the change in the pressure, and the density also there can be a density plus the change of the density. So we can write this equation to this equation. Okay, so again we expand the previous that equation and just retain the first order term or neglecting the higher order term, so we can express the equation. So this is, you can try it out by yourself. Okay, maybe in the textbook it's quite simplified, so you can try it by yourself because like I said, derivation is common in fluid mechanics. Okay, and then we know that this is relationship from the isentropic flow process. Okay, this is the relationship we have looked previously. Okay, in terms of the isentropic flow process, this is the relationship that we can get. So we can just substitute into the above equation, and the equation can transform to this equation. Okay, where we have the velocity, we have the K value, okay, we have the P rho, and also with the change of the rho, or the change of the density equation. Okay, and also, okay, from the previous equation, and also we know that from the continuity equation, okay, we have the term previous in the previous equation, we have the term del rho over the rho. So with the del rho over the d rho over the rho, not del, okay, the d rho over the rho. So we should come with this expression from the continuity. So it will be go to the other side to the right side, so it can become negative. So we just substitute into the equation and we can rearrange the equation so we can get this expression. Okay. Okay, and then also because we want to relate with the category of this flow, okay, whether it's subsonic, supersonic, so that's why we have to come with this the relationship with the Mach number. Okay, and we know also from the speed of sound, okay, you go back to the speed of sound topic, you can see this equation, okay, before we get the general speed of sound equation. So this is equation, okay, for the speed of sound. So you can see here, and we can know we have this equation in this equation, okay, this expression of the speed of sound in this equation. So we can just replace it back. So we can get in terms of this v square over the c square, and because we know v square over the v over the c is the Mach number, so we can replace the Mach number inside this expression. So we can see that we should have three terms, one related to the dv over the v, one related to the m square with the Mach number equation, and then we get another terms related to the area, okay, change of the area. Okay, this is change of the velocity, change of the area, and in the middle here we have this Mach number relationship, okay, terms. So we are going to see how from this equation how we are going to design, okay, or what design of this, or whether we want to apply the converging or the diverging section for our system, for our flow system. So we are going to actually see how we can use this equation to have whether to accelerate or decelerate our flow. So this is very important equation on the how the design of this duct or the channel will influence in terms of whether we can accelerate the flow or the decelerate the flow. Okay, so we will look in the next part. Okay, that's all. Thank you.